Good morning, all. This is Mrs. Padmashri from SNS College of Engineering. Today, I am going to explain the concept batch normalization in deep learning. So, in short, we will call it as BN. Batch normalization is an algorithmic method mainly used in deep neural network. This normalization network is very fast and it is more stable. So, it consists of a vector. We can call it as a normalized activation vector present in the hidden layer. So there are two uh, variables that we are going to use it for the batch system, that is a mean and variance. So the normalization step is applied either before or after the non-linear function. So there are two things that we are going to see today. How will we train the network with this batch normalization concept, and how we will evaluate the network. These two concepts that we are going to learn today in batch normalization. So then we are going to apply this batch normalization concept in each hidden layer present in the deep neural network. So we all know that the architecture of the deep neural network, it has a input layer and number of hidden layers. Then the last will be the output layer. So hidden layer can be n number. So this normalization, we are going to apply it for the hidden layer in order to normalize the output. So the meaning of normalization is we have to improve the performance of the network. So and these are the some of the variables that we are going to use it in the hidden layer to normalize the output, which means to improve the performance, or we can say to improve the accuracy of the network. The first one we consider is mu, is a mean. Mu is called a mean, and sigma squared is called variance, and the normalized output is z norm, okay, to the power I, and the other, the desired output z cap. So these all these four variables that we are going to use, these terms we are going to use to normalize the data, the input data which is given to the hidden layer. So mu, there is a formula for all these four terms. Mu equal to 1 by n into summation of I z of I. So 1 by n, we usually say it is a slope value. 1 by n is a slope value, and sigma squared equal to the variance. Sigma squared is equal to 1 by n into summation of I z I minus mu, the whole square. Okay. So this mu, it takes the value from the mean value from this formula, and it computes the value of z I minus mu, the whole squared. And the normalized form of output is represented as z norm, which is equal to zi minus mu divided by square root of sigma squared minus epsilon. Epsilon. So I'll explain in the coming slide what is this epsilon refers to. Then the desired output z cap equal to alpha into zi normalized output plus beta. I'll be explaining what is this alpha, beta and epsilon in the coming slide, right? So the batch normalization, what it actually determines the mean value variance of activation values across the batch. Here, why we are calling it as batch? That is the main thing that we have to discuss here. So initially, the basic architecture, the basic network of deep learning, we'll be considering the input as individual input. Say x1, x2, x3, x4. All the four or five, it can be till xn, right? So all that are the individual inputs we are considering, and that inputs is we are going to transmit to the hidden layer, from hidden layer to the output layer. This is what the normal deep neural network does, right? So instead of sending or considering each and every individual input, here in batch normalization technique, what we are going to do is we are going to transmit the inputs in the form of a batch, in the form of batch. So what can be the advantage instead of sending individually or one after completing one input, the next x1 weight will be calculated along with that bias value will be added. Then it sends to the activation function. From activation function, then it again goes to the output layer. So this has to be done for n number of inputs, right? So what we are going to do is we are going to consider all the inputs in the form of batch 1, batch 2, batch 3. That is the we can say a bundle of inputs. Okay, so this reduces the complexity of the network as well, which improves the performance and accuracy of the output. Okay, so the again this is the concept. What is this batch normalization? So again we'll come here. It normalize the activation vector z of I, z to the power I, and each neuron's output follows a standard normal distribution across a batch. I'll be showing you the architecture, then it will be very clearly understandable how the batch normalization is working in this neural network. So batch normalization, the first step, see here the picture that you're seeing is n number of input. As I said, the deep neural network, we have n number of input. See, all the networks are bundled. That is, they are made in the form of batch. That is represented as B. So again, we are going to transmit that to the next layer. The next level layer, we know that is a hidden layer, and this the graph represents the activation function. Then after that, the BN batch normalization is done here. Then it is again we are transmitting to the next hidden layer. From there we are sending it to the output. So here you can see here the output that you get here. This is only for 3 neurons, right? So here we have 1, 2, 3 neurons, and we are going to take the output of only the 3 neurons here. So that will be sent in the form of a batch. Then see the last output, complete sine wave we are getting, which is called a normalized output. It is not partial output. See here we have a partial output because the inputs are not normalized, because we have not applied any normalization technique in this particular part. Only the inputs are transmitted. The neurons sends the input to the next layer, that is hidden layer. Hidden layer we have a batch. We are forming batch bunch of input. Then it is transmitted to the output, which we call it as it is not normalized output. But when we transmit through the B and batch normalization node, the output is normalized. Each neuron follows a standard normal distribution. That's what the network says here, architecture. And perceptron functions, the neuron function, it calculates the output z to the power I layer output, applying a linear transformation of alpha and beta. Here, as I said, that I'll be telling you what is alpha, beta here. Okay, alpha is a standard deviation, allows to adjust the standard deviation, and beta allows to adjust the bias value, shifting the curve on the right or on the left side. This is the perceptron function, and here you can see the benefits of alpha and beta parameter. Modifying the distribution allows us to use the different regimes of non-linear functions on the bottom. Okay. So this is the training part. At each part of the iteration training, network computes the mu value and the sigma value. Okay. Then it trains the alpha and beta through a gradient descent. So actually I've explained the gradient descent in my previous video. If anyone has any doubt about this concept, you can go back or you can check my previous video, gradient descent using an exponential moving average, EMA, to give more importance to the latest iteration. So it means in each iteration the values of mean, all the four formulas I showed at the beginning of the slide. So it calculates the mean, mu value, sigma, variance value, then z of I, it's a normalized output, then um, cap, z cap, the desired output. So what we can do, we can easily come check what is the desired output and what is the normalized output here, and also it calculates the gamma and beta values also. This is the training part. So the training part, this is the first part where we apply the concept. Okay, the where we apply the batch normalization concept. Next is the evaluation part. So unlike training, we may not have a full batch to feed into the model during the evaluation phase. We are not going to feed entire batch. What we are going to check only the final values. To tackle the issue, we are going to compute the pop, mu pop, and the sigma pop values, means which is a estimated mean of mu pop is the estimated mean of studied population. Sigma is the standard deviation of the studied population. Okay. So the batch normalization, which allows us to set each parameters independently, and the most important is the vector size. So it should be like we can set how many neurons are in the current hidden layer for multiple layer perceptrons. So concept like when you have a multiple layer, we can able to check how many neurons can be present in each layers, hidden layers, and how many filters are used in the current, how many filters are used in the current hidden layers. That is for convolutional network. So the rest of the concept will be discussed in the next class. Thank you.